a hotel card-activated switch. This is the switch mechanism that when you go into your room and you've got your keys attached to a big plastic card to make it awkward in your pocket so you don't take them away with you. When you get into the room, you pop the card in, and if you listen when I slide this in, I'll hold it up to the microphone. Did you hear a very slight click? It activates a relay that is capable of switching. What's it capable of switching? It's rated 1,800 watts resistive and 800 watts for inductive loads. So I suppose it could control a small heater, but it's mainly designed for the lights. It could also control a contactor that would switch power onto air conditioning and heating and stuff like that. But when you take your card out at the end of the day, or if you're going out, after a delay of 30 seconds, it cuts the power back off again. It's got a courtesy sort of exit delay before it cuts out. There it just cut out. It's very quiet. It sounds like a very small relay. Let's find out. Let's open it and see what's inside. So I've just unplugged it. I shall disconnect these wires. I was going to connect a light to it, but the ferrules I've got in these wires were not having it for getting two wires into the neutral. And to assemble this, it has two little tabs here that push out. It's quite odd, actually, the way it's put together. It's not terribly convenient. This is actually how you're supposed to install it. But you push these down, and you push these down too. I believe this is how you're supposed to install it. It's not easy getting that out. Maybe this is why they were selling them off at Screwfix or Tool Station or whatever it was. That is not easy. That's just going to end up in stuff being broken. And the other side is now popped out rather predictably. Okay, is that going to do it? Yeah, that's going to do it, I think. Okay, so there is the module. Another thing worthy of note, does this click up the way? Mention something does, it clicks up the way. Oh, it's an LED. There was an orange glow that illuminated the little, they've got a cutout here of the arrow and the matching arrow print on the other side. It just makes it glow orange. I'm seeing a photo detector at the bottom of the look of it. So it looks as though it's using infrared as an optical detector instead of a switch. Let's see if we can get any further in with these tabs here maybe. Oh, that's looking promising. That comes off. These little tabs here come out. These are definitely the ones that would break. So I'll pop them out. Same again on the other side, yes indeed. Same again on the other side. Pop them out. And we'll see what the circuitry is. I would expect it to just be something very simple, like a voltage threshold detector. It's a fairly big circuit board. It's got a little daughter circuit board here with the infrared sensor on it. Let's get that out. Let's zoom down a bit because I'm far away here, but not too much. Otherwise I'll wander off shot. So let's undo this. Quite big terminals, they're quite chunky. I wonder if this has other purposes. They were kind of getting rid of these at a sort of low price. That's what kind of, well, someone mentioned that they were selling them off and suggested that it would be good to take one apart. I think it is a good idea to take one apart. This little thing, this little circuit board, oh, it's just unclipped. Oh, it's just kind of pushed into that little window. It's not really clipped in tightly. There's the relay. It's quite a big relay. It's like a finder relay. There's a capacitor for the capacitive dropper and inrush limiting resistor. So most of the circuitry on this is going to be a power supply. I can see a metal oxide varistor here in sleeving, but with a thermal fuse on it. That's kind of important. And then that little daughter board that comes off, right, tell you what, I feel a great need to reverse engineer this. I shall do so. One moment, please. Okay, the reverse engineering is complete. It's done the very modular approach. It's got a power supply board and switching board, and then it's got the logic board with the actual light sensor on it. So the way I've drawn this out, this time I completely forgot to flip this. I usually flip this over so it correlates, everything correlates to the top of the circuit board, but I didn't do that this time. This is good in a way because it lets you see why it's so much easier to reverse engineer when you flip the image over. But what we have here, we have notable things. We've got a big white relay. We've got a thermal fuse, which was actually on this metal oxide varistor. We've got a capacitive dropper based on this series resistor, a capacitor, and then there's a discrete bridge rectifier under here, hidden underneath this, and then there's a Zener diode, a smoothing capacitor, and just a decoupling capacitor for sort of suppressing glitches and transients. The arrangement is shown here. Here is the dropper capacitor with its 470k resistor. There's the sort of inrush limiter and sort of, I suppose, ultimately a fusible resistor, 33 ohms. Then the discrete diode rectifier and the smoothing capacitors. That is it. There's not much to it. The only other thing that's worth mentioning on this is it's got a 4-pin connector. The two middle pins are common. They're the negative. You've got a positive pin, and then you've got the relay switching pin. The relay is already connected here to the positive. So one end of the relay gets switched to negative on the little tiny circuit board. I shall bring in the tiny circuit board picture, and then I'll show you the reverse engineering of it all. I shall flip this over because it makes, that's probably not really, yeah, it doesn't really matter, it's good enough. It's based on a microcontroller. That kind of spoils all the fun because it's all done in software. I thought it was going to be something like an LM324 dual op amp, but it's not. It is a microcontroller they've used for this, but I suppose that allows them to do things like the light sensor, which is based over here. That's this little fork light sensor. It detects a object passing in between that slot. It could be influenced by external light, and if they just used an op amp, that could have been influenced by that. So they've got the facility in the microcontroller to presumably look at the output of that at sort of analog voltage and actually regulate for detecting if there is external light influencing it. Things worthy of note in this. Here is the 4-pin connector that matches the other circuit board. There is a 1k resistor, limited current, and then there's a Zener diode that drops the voltage from 24 volts down to 5.1 volts. That's a standard Zener value. That 1k resistor gets very hot. Other things worthy of note, here's a transistor that switches the relay through this sort of pin here, and there is, between the positive and the relay control, there is a back EMF spike suppression diode to actually block the back EMF spike from the diode, from the relay, should I say, from damaging this transistor. Other than that, there's not a lot. There's an electrolytic in the back, there's a couple of decoupling capacitors. This one may actually be part of a reset circuit. I shall show you the circuit diagram, that's the best bit. So we'll start off, I'll zoom down this. We shall start off with the power supply. We have live, load and neutral. Between live and load is a relay contact. Live then goes through a thermal fuse to feed the rest of the circuitry, and it's actually coupled. See this dotted line? It was actually in a bit of heat shrink sleeving to actually squeeze it tightly onto the side of the metal oxide varistor. The metal oxide varistor is a 14D471K. That breaks down to 14 millimeters diameter, D disc shaped, 471, 47 and 1 is a multiplier, so that's 47 and a 10 is 470 volts. That's the voltage at which it will start conducting. Because the metal oxide varistor is designed to clip high voltage transients. If they exceed its rating, it goes down, lowers in resistance, and that shunts that spike. The reason there's a thermal fuse coupled onto it is because when these fail, they often start conducting and they can get very hot, and that's going to trip out the circuit and kill it. The next thing it goes to is this 330 nanofarad capacitor with a slightly undersized quarter watt resistor, 470k underneath it. Oh, you know what? I've missed a bit here. I'll just bodge it in a wee tiny resistor, 33 ohms. Yeah, I missed a bit. But there is that series resistor which acts to limit inrush current, and also it acts as a fusible resistor if everything else goes kaboom. There is the discrete bridge rectifier. It's those diodes that are just stuffed under here. Then on the other side, there's a 24 volt Zener diode which caps the voltage to 24 volts, a 220 microfarad 50 volt capacitor, and then a decoupling capacitor, probably 100 nanofarad. And then there's the relay coil. Things worthy of note. The voltage I measured was actually about 23.5 volts. When the relay is active, it drops to 17.5. Now, the thing about relays is, although it takes their full rated voltage usually, well, fairly close to that to bring them in, once they've actually pulled in, the magnetic contact is such that when it's closed, it doesn't require as high a voltage. So they've balanced that. They've chosen a capacitor there that will actually provide the 24 volts by charging that capacitor up to the full 24 volts. But once that's kicked in, it's just enough to actually sort of hold that relay in. And that means it reduces the amount of current through the circuit, and that takes the stress off this Zener diode, which is coincidentally right next to the electrolytic capacitor. That's just as well it's running cool. Next bit of the circuitry. So we get the 24 volt going out, we've got the relay control going out, and we've got the 0 volt going out. Now it's the turn of the tiny little circuit. And the first thing that happens when it goes onto this circuit is it goes through a 1K resistor. Now, it starts off about 24 volts, it's dropping it to 5.1 volts. That means about 19 volts is being dropped across that resistor. And that means that 19 milliamps will flow through it. 90 volts times 90 milliamps is about 360 milliwatts. That resistor was getting very hot. I looked at the circuit running with the thermal imaging camera. I was expecting the Zener diode in here to be getting hot. In reality, the hottest component, the whole board, was this resistor here. And it was running at about, I think it was about 80 degrees Celsius. It was very hot. That, to me, is the failure point of that circuit. It's going to really stress that resistor. So we get the Zener, and then we get a smoothie capacitor, 100 microfarad, 60 volt, another decoupling capacitor, probably 100 nanofarad. Then we get the microcontroller. The microcontroller is a 69P801X. I didn't find that on Google. I found a reference to it on a Chinese site. That was all. I'm not sure what it is. Very similar pinout to a PIC 12 type microcontroller. There is a resistor, charges a capacitor. That could be a timer, or it could, well, it would be a timer both ways. It could be a clock oscillator, but it's most likely just a reset pin. And given the pin it's connected to, I think it is most likely just a reset circuit to ensure that this processor is held in a reset state while the power stabilizes, particularly given the way it's based on resistors and Zeners and capacitors and things like that to actually drive that supply. It's not just going to suddenly appear 5 volts straight away. The processor controls the little orange LED. That's the one on the satellite circuit board here. And it's the one that shines through this channel here and makes this little arrow light in the front. It goes out when you put the card in. It doesn't really need to do that. It's kind of pointless. I can't help feeling they could have actually cheated this. If they hadn't controlled that LED, they could have actually stuck another resistor in parallel with that one and raised the value of that and actually stuck an LED in there. And that would have allowed them to power that LED without any other losses. And it would have taken a bit of the stress off that resistor and meant they could power that LED at a fairly decent brightness. The other LED that's controlled by the processor is the LED and the optocoupler, and these both have 3K resistors, which, when you think about it, it's a very low current. It's unusually low current for the optocoupler, the slotted optocoupler. But it fires infrared beam across in that coupler, and then I'm guessing it might be a phototransistor. This is purely a guess here. I'll just put a wee question mark next to it to show that. It forms a potential divider with a 10K resistor, and then it goes back to the processor. And I'm guessing that the processor is turning that LED on and off. I don't know if it's modulating at high frequency or just comparing light to dark. But it looks for the response from that. And if it suddenly sees a significant change, it knows that a card has been slotted into the slot, and it starts the time delay. When it does start the time delay, the output goes via this orange dotted line to this transistor, which was an L6, was it not? L6. Fairly standard NPN transistor, 4K7 base resistor to limit the current, and it switches the relay. And there's the back EMF diode that is effectively across the relay, because the relay, which is off another board, is wired like that. And what happens with these relays, you need that back EMF diode, because when the relay is turned on and this end is positive and this end is pulled negative, it builds up a magnetic field as it brings the contact in. When you turn it back off again, the field collapses and this effectively goes negative and this goes positive, but there's no load in it, so you end up with a very high voltage spike referenced to 24 volts, and that can actually cause damage to the transistors. So by putting that diode there, it shunts that past, it just basically bridges it out, that back EMF spike. And that is it. It's an interesting device. Very interesting. I'll tame this down. So it's very modular. It seems quite well made, apart from that slightly hot resistor. That there's plenty of space, they could have done that. They could have spread it across a bit. They could have put two resistors in series or two in parallel, or done what I've said there with the LED that's kind of off board. Very strange. But that is it. It looks quite a complex unit to make. And I wonder if the reason that this is a universal power board with a relay is because it means that they can actually have other functions. You know, they could have other modules that get soldered into it, and they have like time delay functions for other applications, or a push button time delay, or just random functions. It's possible they've just basically covered the option that they could have actually made various devices using a standard circuit board. LAP, L-A-P. But there we go. That is the hotel card detector that turns the power to your lights and potentially heating and air conditioning on while you're in the hotel room. But as soon as you leave and you take that card out, my stomach has just made a loud burbling noise there. When you take that card out, it gives you that 30-second time just for the convenience of leaving the room before it turns all the lights and everything off.